Hello, this is Professor Keen. I'm continuing my discussion of Pascal's treatise on the vacuum. Today we're going to talk about Pascal's principle. This is from chapter 14 of A Student's Guide to the Grade Physics Texts. And so what we're going to be doing is beginning by talking about something by way of background, and that is the hydrostatic paradox. So what I'll do is I'll talk about the hydrostatic paradox. I'll explain what I mean by that in a minute, and then how Pascal attempts to explain the hydrostatic paradox, and by that way we arrive at Pascal's principle. So what is the hydrostatic paradox? I'm going to write some of this stuff down. So we're going to talk about the hydrostatic paradox. And this was something that Pascal himself did not come up with. It was Simon Stevinus. You might recall that we came across Simon Stevinus once before in this class. He is the one who has the epitaph of Simon Stevinus on his gravestone that Galileo had talked about. You might remember the epitaph of Stevinus where he drew a ramp like this, and then he imagined a string of beads, and the ramp was just long enough to fit, let's say, 4 beads on that side and 2 beads on this side, and you attach these by a string like this, and then the string of beads hangs down beneath this ramp like this. And what Stevinus did is he used this to explain why it is that 2 beads over here can balance 4 beads over there so as to create equilibrium. Well, so we are not going to be talking about the epitaph of Stevinus today, nor will we talk about the other thing that he's famous for. The other thing that he's famous for is that he introduced Europe to the Arabic notion of the decimal system. You might recall that when we were studying Galileo, he never used decimals. Well, that's not a coincidence. The decimal system was not really introduced into Europe until the time of Stevinus. Stevinus was roughly contemporary with Galileo, and so after the work of Stevinus, then the European scholars began using the decimal system. So we're not going to be talking about specifically the epitaph of Stevinus today, and we're not going to be talking about the decimal system directly, but we are going to be talking about the hydrostatic paradox. So what is the hydrostatic paradox? Well, over here in the text, let's jump ahead to 2 pages in, and Pascal talks about the hydrostatic paradox in these figures right here, and he refers to that in the text on page 178. So let me explain what the hydrostatic paradox is. So imagine for the moment that you had a cylinder full of water. So I'm going to draw a cylinder like this. I'm getting used to drawing on this tablet, so you have to excuse the not entirely straight lines. But imagine you had a cylinder like this, and you plug the bottom with a cork, but this is a cork that is able to slide very easily up and down. And let's suppose that you filled this with water. So this is H2O in here. And let's suppose the diameter of this cylinder is such that the cross-sectional area of the tube is exactly equal to 100 square inches. And if this water is 28 inches tall, then the weight of this water is going to be exactly 100 pounds of water in this tube. And that is because 28 cubic inches of water weighs about 1 pound. oops, 1 pound. So there we have 2,800 cubic inches, and so we have about 100 pounds of water inside of a cylinder. And because we have this little plug in the bottom right here, we would need to apply a force to the bottom of exactly 100 pounds in order to support this column of water. If we didn't apply a 100-pound force, this would all pour out. Now, this in itself is not the hydrostatic paradox. This is just sort of common sense. Here is the interesting thing. Here's where I'm going to introduce the paradox. Let's suppose now that we had, instead of this wide tube, we have a very narrow tube that opens up into a wide region on the bottom. So here we have a very narrow tube like this. And again, this is a cylinder. You have to think about this as being cylindrical. And the bottom of it has a diameter so that the area here is also 100 square inches. And we put a plug of the exact same size as this other plug into the bottom. And we filled this very narrow tube up to a depth of, again, 28 inches. And let's suppose at the top here, the diameter is very narrow so that the area at the top was only 1 square inch. So this is like a very long, thin neck opening up into a wide neck at the bottom. And let's suppose this is narrow enough so that in here you only have about 1 pound of water. Yes, I know it opens up in the bottom a little bit, but if this is a very small region, then let's suppose you only have 1 pound of water in here. Now the question is, how much force does it take to support that 1 pound of water? And you might guess that it would only take 1 pound of force, but you would be wrong. This takes also 100 pounds of force in order to support that 1 pound of water. In other words, if the depth of the fluid is the same in this narrow column and the wide column, and we have the plug that has a cross-sectional area of 100 square inches here and 100 square inches over here, then it's going to take the exact same force to support the water in both columns. This is the hydrostatic paradox. So why does it take 100 pounds of force to plug the bottom hole in both cases? This seems paradoxical, and that's why it's called the hydrostatic paradox. And after having introduced you to that, and I have run out of space on this worksheet, and so what I'm going to do is I'm going to pause the video, and I'm going to start up again in a moment.